Sure. Okay, our next presenter is Ahmed Abdul Mohsen. He worked with me and he's presenting his work on GCAC environment simulator. That's a title, that's GCAC. That's GCAC.
Okay. How's everybody?
Very good.
Everybody's going to pay $1 on their way out after this. Too much information. So this is my senior project. I work with Dr. Mazami. It's a GCAS thermal simulator for the GCAS system. This is my outline. I'm just here showing what I'm going to go over. It's not a lot of stuff. I'm going to go through it very fast. So just to explain to you what GCAS is a system that was built at NASA, and it has 2 spectrometers in it, and that system flies in airplanes and measures different pollutants using different, measuring different spectrums and using the 2 spectrometers between ultraviolet and near infrared. So right here, this is the GCAS system itself. This is right here is the spectrometer. There is another black one down there. Right here, this is the 3D modeling of it. And my project, or what I was supposed to do, is I needed to build something to simulate the flight environment, simulate that in the lab, so we can be able to set our spectrometers to whatever we want it to be before, and test it before even flying and getting data, because that makes a huge difference. And spectrometers varies, the operation of it varies very much with different temperature. We want it to be at the 22 degrees centigrade through the whole time. So the background of this project, actually nobody tried or attempted that before, and the team that was using the code 614 at NASA, they were just using an air conditioning and pointing it towards the system to cool it down, and that wasn't very sufficient. These here are graphs from the flight system. Right there, it shows this is the altitude, and you see if the plane goes up, the temperature goes down. If the plane goes down, the temperature starts going up. Each of these curves represent a different thermos inside the system. This is the same graph, the previous graph, but I just broke it down to look better. So this right here is the temperature of the wing, and this right here is the red is the temperature of the wing. The black is the temperature of the cover. This is the altitude in feet and 1,000 feet. And this is the temperatures inside the GCAS. And as you can see, once you start flying higher, the temperature starts stabilizing. And like I said, these are 4 different thermostats inside the system. Why simulate the thermal environment? Again, like I said, we need that to make sure that we will have a consistent performance. We want to keep it at 22 degrees centigrade. And this says that in flight we accomplish that through using external air that is cold, and in the lab we need to regenerate that to be able to set our systems. This is my methodology. It's basically this formula right here tells you how much airflow in cubic feet that you need to be able to cool down a certain amount of wasted heat. So our average consumption, our system maximum consumption of power, which is 669 watts, and then this is the average consumption, and our system power conversion efficiency is 85, so we're losing 15, so this is our max, and this is our average power loss. When we do that, when we use that previous equation, we find out for maximum we need 3.9 cubic feet per minute. For average, we need 1.9. That's when I went out and looked for specific coolers, and that cooler provides 4.3 feet per minute, and that's the cooler that I picked. Used two of them because of the mechanical design. That one of the spectrometers is a little bit higher, so it blocks the air from one side to the other. This is another graph that shows you how I picked that, why I picked that specific cooling system, because if you look right here, I want to be at 22, and I want to be there when the ambient is 22, I want to be there at 0 degrees centigrade. So it brings us down here, which is between 80 and 120, which is mostly 100, and that's my maximum loss, and that's what I need to cover. This is the AutoCAD design that I use. I used more than one program. One of them was AutoCAD. This is the cover that I designed. This is another 3D model of the cover sitting on the base to make sure that it's airtight. These are, we were planning on doing it in thick sheets of aluminum T9, I think, and then that was going to be so heavy, so I came up with that quadruple double edge frame design, which, if you can see, there's 2 edges right here, and there's 4 of them, and then we covered it with aluminum sheets, which saved us like 30 pounds. This is the final design, final mechanical design with the handles. This is after fabrication, right out of the lab, and this is after we put the 2 coolers in there, we put our insulation in there, and this is how it looks at the end. After that, we had to do the electrical design because we need to control that temperature. So these are the controls that I'm using. I'm using 2 of them, one for each cooler to use it independently, and these are the power supplies that I use. This is the electrical design that I did. This is the power supply, control A, power supply B, control B. These are actually 2 cables. One is a circular cable, one is a sub-D cable. Connects to these 2 cables, go to the cooler, and the coolers tick A and tick B at the cover. This is some pictures of the work that we did. These are the circular connectors right here. This is everything was done flight grade, so we can use it in flight. This is the circular cable at the end right here. This is at the end, at the cooler sides. The sub-D connectors. This is at the hot side, or where it's going to get the power. This is the control panel. This is the back of the control panel. This is how it looks on the flight rack when they fly with it. This is our system right there. This is the final product in lab when we're using it to cool the system and to be able to optimize it. Right now, I'll just do some demo. So I'm sorry, you can't see right here, but if you see right here, this temperature is starting at 27, and like a couple of seconds it will go down to like 15, 16. It's going to keep going down till it gets to the number that we wanted where we set it, and this is going to start sending a square signal depending on whatever frequency to keep it at that temperature. It measures the temperature, goes up, starts the outside fan, measures again, it goes to the whatever temperature we want, and stops the system. Back here is, these are the connections that I built. All of this has been done flight grade, so it would withstand vibration and low temperature. So we can use this in flight too, if we're flying over tropical areas where we need to cool it, we will fly. The results, as you can see, this right here is the data we got from an actual flight. for air quality. And if you can see, there is the more curvy curve is the actual data that we got, and the line that goes through it is the average. And this is temperature for housing A, housing B, housing C, which is 3 different thermostats in different areas in the housing, and then the spectrometer, the temperature of the spectrometer. This is what we were able to replicate in the lab for the same test. And as you can see, it simulates it very closely. Of course, some of them we cannot control because it's environment. Maybe it gets a little bit cooler, hotter, we cannot. But right here in the lab, we were able to get to the same numbers at the same range for all the spectrometers. This is another test for ocean colors. And again, the top is the flight data that we got from an actual flight. This is what we were able to replicate in the lab. In conclusion, we were able to replicate whatever we wanted to do. We were able to do it in a very good range. The difference might be less than 0.1 degrees centigrade. That system right now is a crucial part of that other system, the GCAS system. They cannot do they have to do their optimization using this system in the lab. I actually had to borrow it from them to bring it here and show it to everybody. And that's a very good success for this kind of system. Future work, what I'm working on right now, I'm trying to get smaller text and build this to be lighter and a little bit smaller, because the real estate for example, a King Air airplane is so small, so these systems are too big and it's too heavy, so I'm trying to make it smaller so we can use it for tropical flights. Acknowledgement, I can make this list go way longer. First of all, after God, I thank my wife and my family. I thank Dr. Moazzami, Dr. Astaki for putting up with me, Dr. Scott for helping me all the time whenever I go to his office, NASA, of course, USRA, guest star, the team at 614, Matthew, Kent, and Sam. And these are my references and questions. Efficiency difference?
Yeah, you put up an efficiency number before, and
The power efficiency, what we're losing.
yeah, what you're losing, what's the?
Well, what we're losing, we're gonna lose it one way or another, because the system is, once it works, we're gonna lose it. So our efficiency, this is actually, if I go deeper into it and show you the Excel, this is the worst efficiency we can get out of it. We actually get way better efficiency than that. So we are gonna lose that one way or another. If it heats up, the efficiencies, we're gonna lose more. But this is what we're losing in the environment when we're flying. So that's what I needed to calculate for, because that's what I'm trying to replicate. Any more?
Any questions for Ahmed? Okay.
Thank you.
So next presenter is